Okay, welcome to the linear algebra class. Okay, sorry for the delay. And let us consider this section. So we considered the section theorem 2.22, and let me explain this one more time. So what do we have? We have, okay, beta and beta prime are two bases for certain space of V, and okay, so given this V to V, we are considering the identity matrix, the identity mapping. I'm sorry. So the identity mapping is considered. But we consider two different bases. So beta prime as a basis for the domain, and beta as a basis for the codomain. Then and then we can consider the standard representation, okay, from V to some Fn space. And we can find the change of the coordinate base, the matrix Q, okay, from beta prime to beta. Then we have this relation here. So if Q denotes the matrix representing this identity mapping, but we allow two different bases, beta prime for the domain and beta for the codomain. Then when I take this path or this path, you will get the same vector, same result, right? So if I take the blue, then given any vector, you can find, given any vector V in the domain, you can find its coordinate with respect to beta prime. And then if you multiply Q matrix, then what you get is you get the coordinate of the image, right? And if I take the red path, the identity mapping maps V to V. So the image of a V under the identity mapping is V, right? And then its standard representation is expressed by this. But only difference here is that you are using beta as a basis. So both are representing the coordinate of the image, right? But what is the mapping here? We have the identity mapping. So the image of V vector will be V itself, right? But in the codomain, we are using beta as a basis. So the coordinate of V with respect to beta, okay? So both are representing this. So that's the coordinate in the codomain, right? So we already considered this in some general situation, and theorem 2.22 is a very special situation where this mapping is just the identity mapping. And in that case, we have this simple situation. So we already considered this. So here is an example. So in R2 space, if I consider two different bases, beta and beta prime, 2 and 4 vector can be written by this. So the coordinate of 2 and 4 vector with respect to beta is 3 and negative 1, right? So this part shows that given this 2 and 4 vector, the coordinate of this vector with respect to beta is 3 and negative 1, right? And this 3, sorry, oh no, 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 just a second. Yeah, right. And 3, 1 can be written by this. So that means the coordinate of 3, 1 vector with respect to beta will be 2 and negative 2 and 1. So this beta is the coordinate of the codomain. So the matrix representing this identity mapping, okay, identity mapping, but with different bases, beta prime for the domain and beta for the codomain, that Q consists of 3 and negative 1 and 2 and 1, right? Do you follow me? Because this 2, 4 is the image of identity mapping. So this is the image of 3 and 1 vector under identity mapping. So Q is constructed by this. So if I want to find the coordinate of 2 and 4 with respect to beta, okay, there are two ways. You can directly represent 2 and 4 with respect to beta, or so or you can multiply Q with this coordinate, and Q is given above, and the coordinate of 2 and 4 with respect to beta prime is just a 1, 0 vector. So if you multiply this, you get 3 and negative 1. Okay. So this approach considers this blue path, right? If we want to take the red path, okay, then if I, so this is the blue path. So if I number, then if this is the path 1 and here is the second path, then this is this first path. But then how can I find the second path to get this vector? Then you need to find A and B, right? Such that, so for path 2, you need to find A and B such that 2 and 4 equals A times the first vector in beta and B times 1 and negative 1. So in other words, you need to solve A plus B equals 2 and A minus B equals to 4. So you need to solve these equations to get these two numbers A and B. So if I follow these, but that, okay, path 2, then you need to solve a system of equations in general. But in case of the first path, as long as you have this Q matrix, you can easily find the vector result. But anyway, it depends. Depending on the situation, some you may prefer the first path or second path. Now, so for the remainder of this section, we consider only linear transformations that map a vector space V into itself. And such a linear transformation will be called a linear operator on V. And suppose now that a T is a linear operator on a finite dimensional vector space V, and we have two bases, beta and beta prime. Then V can be represented by the matrices this or this. But please remember that this one assumes that beta is a basis for the V in the domain and codomain. This, the second one, is a matrix representing the transformation T when beta prime is used as a basis for the domain and codomain. Now, the question will be this: what will be the relationship, some mathematical relation between these two matrices? So we want to consider such question here. So let T be a linear operator on certain finite dimensional V space. And suppose that we have two bases, beta and beta prime. And Q is the change of coordinate matrix that changes beta prime into beta. Okay? So Q, so given this identity mapping, when beta is used in the domain and beta prime is used in the codomain, then we have the standard representation from V to Fn space. Then between two Fn spaces, we have the matrix mapping Q, okay, which characterizes the identity mapping. So we have such Q. So Q is the change of coordinate matrix that changes the beta prime coordinate into beta coordinate. Then this one will be this. Okay. So before we prove this, okay, prove this, let us consider this mapping. So we have a mapping from V to V. That is a T. Okay. And we have another mapping from V to V that is okay, let me first finish this proof and then let me go back to that image in, okay? Sorry about that. So first, let us prove this. So let I be the identity transformation on V, okay? So this one, that is denoted by I in this slide. Then the composite of T and identity will be just the T. Okay. Then Q representing the identity mapping, and T the matrix representing this T with respect to beta prime. Given this, now Q is the matrix representing this identity, but changes the basis from beta prime to beta. Now T is a matrix representing this beta prime, and this beta prime is a basis for the domain and codomain for both. So actually it is the matrix representing this linear transformation with beta prime as the basis. Now in that case, so we can combine these two matrices with a single matrix. That's what we learned in theorem 2.11. So if I have this, product of two matrices, then I can combine those two products as a single matrix. Now, so I have this single matrix. Now, as I said, I the composite of I and T will be the same as the composite of T and I. So the composite of I and T can be replaced by the composite of T and I. And this can be, by using the theorem 2.11 one more time, I can split this into these two. The first matrix on the right is just the Q matrix, and this matrix on the left is just this one. So, so this product of two matrices will be the same as this, and Q is a matrix representing the identity mapping, right? So Q must be invertible. Right? Please remember that if your matrix is representing certain invertible mapping, then the matrix must be invertible. So if I multiply the inverse of Q, we get this. So actually, instead of this, the what I highlighted is more important. So Q times this matrix will be the same as this. Okay. So what does that mean? What is the meaning of this? Q first changes the coordinate. So this one will represent a linear transformation when both domain and codomain use beta prime as a basis. Okay? And then it changes the basis to beta. On the right, Q first changes the basis. And then we consider this a linear transformation where beta is used as a basis for the domain and codomain. I have I thought so. This Q and so this one considers, given this V, okay, given any vector, this one represents, so given this V space, initially if I have beta prime, given any vector with respect to beta prime basis, given, so given any vector V in V space, I can find its coordinate with respect to beta prime, and then I can consider, I can multiply this matrix, then you get this. So given V, I can find its coordinate, find the coordinate of the image with respect to beta prime, and then if I consider, the identity mapping, then the image, so V from V, you get, so let me rewrite this. Okay, so from V to V, I have a linear transformation T. Then for any V vector, I can find its coordinate. So T over V is here. And then if I consider the identity mapping from V to V, then T over V is mapped to T over V, right? So that is the ordinary mapping. Now, if I consider beta prime as a basis, then from V, we can find its coordinate in Fn space. And if I multiply this, then we get a vector, okay, which is the image of T over V, but with respect to beta prime. Okay. And then if I consider this Q, okay, then it will it will change this beta prime coordinate to beta coordinate. So that's what this Q times the matrix for T with respect to beta prime implies. So given any V, we can find its coordinate with respect to beta prime. Then that is mapped to the image, but that image is expressed in terms of beta prime. And then we change the basis to beta prime basis to beta. Or, so instead of doing this, we can consider this. So instead of doing this, we can consider the identity mapping first. So from V, that is mapped to V. And then I can consider T to get T of V. And if I use the beta basis, a beta prime basis, then I have the coordinate of V with respect to beta prime. Okay. And then if I change the basis to beta, then you get the coordinate of V, but now with respect to beta. That's the standard representation. And then I can consider this Q. I'm sorry, not Q. I can consider this mapping T to get the image of the coordinate of the image with respect to beta. So in the theorem, this Q So this product on the left considers this transformation, this approach, and the vector on the right, the matrix on the right, considers this transformation. So in the on the left, the T mapping, so T mapping is considered the first, and then the identity mapping is applied. On the right, identity mapping is considered the first, and then the transpose, the T mapping is applied. So that's what this theorem 2.23 implies. Okay, so these two will be the same. Okay, so these two will be the same, meaning given this mapping from V, given this mapping on V space, I can consider this T, okay, Ti or identity T, and that can be interpreted like this. So that's the theorem we considered, and in the example, let T be a linear operator on R2 space defined by this, and let us consider two bases, beta and beta prime. And then the matrix representing this beta will be this. It is simple, right? Q can be also easily identified. And given this Q and Q inverse and this matrix can be obtained by multiplying these three. Okay, but actually more importantly, you want to consider Q. This will be this. So probably you will use this idea to get the image vector under with respect to a specific basis. Now here is another example. So here in example, when I consider the reflection about the x-axis, finding the image is simple because I can just change the sign of the y coordinate, right? But if I consider a line like this, and then if I want to consider it's the reflection about this line, then the finding the coordinate of the image is a little bit difficult, a little bit challenging, right? So if I give you any arbitrary point AB, then finding its image is quite difficult. And at that point, we want to use the theorem, okay? Because the reflection about x-axis or y-axis is simple. So we can take advantage of this. Because if I consider this y equals to 2x line, if I use the standard basis, the finding the coordinate is a little bit difficult. But if I choose one vector on that specific line, like 1, 2 vector, since the vector is on that line, the reflection of that vector will be itself. Right? Now, if I consider a vector which is orthogonal to this line, like negative 2.1, then we can also find its image as well, because in that case, the image of negative 2 and 1 is just a negation of this vector. I can just change the sign of x coordinate and y coordinate. So the image of that vector is this one. So that means if I choose 1, 2, and negative 2 and 1 as a basis, then then the matrix representing this reflection with respect to this beta prime will be quite simple, because 1 2 vector is not changed and negative 2 1 vector is reflected to the negative 1 multiple of that vector. So I can easily find this matrix if I choose beta prime as a basis. Okay? So if I use the theorem, okay, given this beta, the standard basis, and beta prime, this newly obtained vector, then I can find the Q, okay, and I can also find Q inverse as well. Then this matrix representing T with respect to the standard basis can be obtained by multiplying these three matrices. That means if I give you any vector, you can easily identify the coordinate with respect to the standard basis, and then if you multiply that vector with this matrix, then you get the coordinate of the image with respect to the standard basis. So this example gives a very useful hint. Okay, the standard basis may not be useful in some linear transformation like this, but for that specific linear transformation, we can choose a very simple basis. And with respect to that simple basis, we can find the matrix T, matrix for T, or matrix Q. Then by multiplying these matrices, we can find what we want. I mean, the matrix representing this linear transformation with respect to even the standard basis or even any basis. So, so given this product of three matrices, if I give you any point on the plane, all you need to do is you can just multiply the matrix, and that is the coordinate of the image vector, which means that is the coordinate of the reflection of any arbitrary A and B vector. Now, at this point, note, note, in R2 or in Rn space, if beta is the standard basis, for any x vector in R2 or even Rn, so let me change this to Rn space, if beta is the standard basis, then for any x, the coordinate of x relative to the standard basis will be the same as x, right? So that's why the image of this is actually the same as the coordinate of this image with respect to the standard basis. Okay, so that's what, okay, so this matrix times the coordinate of the vector. So this is the coordinate of the image. Okay, so if I call this guy as v vector, then this is the coordinate of v with respect to the standard basis, and this is the matrix representing this T with respect to the standard basis. So if you multiply these two, you get the coordinate of this image with respect to the standard basis, which is just the T of A and B. So here, as a corollary, if A represents certain n by m matrix and if gamma is on ordered basis, then if Q is the m by n matrix whose jth column is the jth vector of gamma, then this Q is representing the identity mapping. Okay, in other words, this Q, okay, just changes the basis from the ordered basis to the standard between the ordered gamma and the standard basis. So the matrix representing this left multiplication by A with respect to this new basis the gamma can be obtained from the matrix representing this transformation with respect to the standard basis, right? So A is the matrix representing this L sub A left multiplication mapping with respect to the standard basis. And Q is a mapping which changes the basis between Q, the gamma, and the identity mapping. Then we have this simple result. So as an example, given this A matrix, and gamma, and Q inverse, this matrix can be obtained by multiplying these three matrices. Okay, so A and the matrix at the bottom both are representing L sub A matrix. So this is also representing L sub A matrix, but A is representing this L sub A with respect to the standard basis. While the matrix at the bottom is representing this same linear mapping but with a different basis, gamma. So we just observed that given these two matrices A and B, one matrix was represented by this form where this Q is a certain invertible matrix. Now if that happens, then we say A and B are similar. Okay, so if we say A and B are similar, if there exists an invertible matrix Q such that B equals Q inverse times AQ. Okay, I mean, if B is similar to A in this sense, then A is similar to B because A can be written as Q, B, and Q inverse, or P inverse B, P for P representing this Q inverse. So if B is similar to A, then A is similar to B, so that we say A and B are similar each other. So this similarity means similarity between two matrices implies that there exists certain invertible matrix Q. So this Q doesn't have to represent the identity mapping. Okay, so here in this definition, Q can be any invertible matrix. So if you can find such Q satisfying this relation, then we say A and B are similar matrices. And okay, so that's the end of section 5 of chapter 2. And just a second, I have. Mm, Okay, so that's the end of the section. So as we as I announced on the first day, or as you can find the updated syllabus, we have the midterm on April 21st, right? I have, yeah, April 21st from not 9, okay, 10:30 to 11:45. And this is the offline in-person exam, okay? And you need to come at the Hana Science Hall, room B207. B means basement. Basement room 207, not second floor. So please come to this room on April 21st, okay? So there is no Zoom class on 21st. You need to physically come to the classroom, okay? And the coverage, and it covers from section 1.1 up to section 2.5. Okay. And this is the closed book, closed notebook exam. No electric devices. Okay. So you cannot bring cell phone, tablets, laptops. Those are not allowed. Okay. And what else? Oh, the number of problems. Um, Not determined yet. So I don't know yet. I mean, I need to make the problems during the weekends. And so depending on the types or the difficulty, the number of problems will be determined. Now for the types, there may be, okay, okay, true false problem may be given. Say something like, say 2 is an even number, something like that. I mean, so if you believe it is true, you can mark it true. If it is false, you can mark false. Okay, so some true false problem may be given. So some simple calculation problem. When I say simple, then usually if it requires, say 5, 6 lines of calculation, then I think it is a simple. Okay, so no, depending on the approach, say, so usually less than 10 lines of calculation. Okay, then I believe then it is a simple. So such questions may be given, and I may ask you simple proof, but I'm not asking the theorems in the slides or textbook. I may give you some statement and I may ask you to verify the statement is correct. And for that one, usually it also require, if it usually it takes about 4 to 5 lines of statements will be sufficient. Okay, so I do not say I do not give some theorem in the textbook. Say if I give you theorem 2.23 and then if please prove it, I do not give such question. Okay, I will assume that you understand this 2.23. Okay, and using this theorem, you can prove certain simple situation or some application. Okay, so if it takes say 4 to 5 lines, then probably that may be a possible question. And what is so? Just a second. Okay, so that will be given, and what else? So some simple calculation, some simple proof, very simple proof, very simple. Okay, I don't like a lengthy proof in my exam. So, and what else? So those will be given. And next time, so on 23rd, on Thursday, I will show some simple problems, sample problems some students are asking. So on 23rd, so there is class on 20, okay, this is for, oh, on 16th, so not 23rd, sorry, on April 16th, and on that day I will show some sample problems. Okay, so some sample problems in the past, so that, but those sample problems may be modified. Okay, in this coming exam. So I will show you some sample problems. Mm, yeah. So this is the information regarding the exam. So as I said, you must come to this room on 21st physically. Okay, don't be late. Okay, the exam starts exactly at 10:30 and it will end at 11:45. So, and if you have any questions, okay, regarding the exam, please email me. Okay. And what else? Well, yeah. Okay, so that's it. Okay, and then for the remaining time out for today and 16th, let me consider a little bit of chapter 3. Okay, and as I said, the exam midterm covers up to section 2.5, not the chapter sections in chapter 3. Okay, so even though we consider this chapter 3, this chapter 3 will be covered in the final exam. Okay, and sometimes some students think that this chapter 3 is related with the midterm, but that is not related, okay? So please do not use any concept introduced in chapter 3 in the midterm. It is not required. Okay. So section 3, chapter 3 in section 1 start with an elementary matrix or elementary row operation. Okay. So suppose that A is on any m by m matrix. Now we want to consider following three operations. So given two rows of A, sometimes I will interchange these two rows. Okay? Or sometimes I will multiply some non-zero number to certain row. Or I multiply certain number to some row and then add it to another row. Okay, these three operations will be simply called interchange, scaling, and replacement. Okay, and these three operations will be called elementary row operations or simply elementary operation. Now, in the textbook, the definition allows similar operation on columns. So, yes, we can apply the similar operation to columns, meaning I can interchange two columns of A, or I can multiply some non-zero value to a certain column, or I can multiply some number to a certain column and then add it to another column. That will be called elementary column operation. And the interchange operation will be called in this textbook the operation of type 1. The scaling operation will be called of type 2, and the replacement operation will be called type 3. But this type 1, type 2, type 3, this numbering is quite unique in this textbook. Okay, if we read some other linear algebra textbooks, they don't say type 1, 2, or 3. They may say interchange, scaling, or replacement. But in this textbook, the author prefers type 1, 2, or 3. So let us use this expression. But as I said, these expressions are quite this textbook unique, or textbook specific, meaning other textbooks do not use type 1, 2, or 3. Now, before I go to the next part, next slide, let me go back to this. So interchanging any two rows. So as I said, I will focus on the rows. So interchanging two rows. That is elementary row operation or type 1. Okay. And what happens if I re-exchange those two rows? For example, given a matrix, if I interchange the first row and the third row, then third row becomes the first and the first row becomes the third. Now, if I re-exchange these two, then you go back to the original situation, original status, right? The second operation multiplies a non-zero value to some row. Okay, so you multiply some non-zero number to a certain row. Say you multiply 2 to the second row or 3 to the fifth row and so on. Okay, and that is called the scaling operation or type 2 operation. I multiply non-zero value. Okay, so let me give some example here. So if I have, say, 1, 2, 2, 4, and say 3, 0. Interchange means I can interchange, for example, the first row with the third row. Then type 1 will change the matrix into 3, 0, 2, 4, 1, 2. Okay? Or if I multiply non-zero value to this matrix, say if I multiply 3 to the second row, then the matrix will be 1, 2, 6, 12, and 3, 0. So the second row is changed by 6 and 12. Now, since I multiplied non-zero value, okay, so here I multiplied 3 in this case. If I multiply its reciprocal, the reciprocal always exists because I'm considering a non-zero value. In other words, if I multiply 1/3 to the second row, you get 1, 2, 2, 4, and 3, 0, the original matrix. And as I said, I interchanged the first row and the third row in type 1 operation, but if I re-interchange these two, you go back to 1, 2, 2, 4, 3, 0. That's the, so I can go back to the original status by interchanging the two rows again. And in case of the type 2 operation, when I multiply certain non-zero value to some row, when I multiply the reciprocal of the scalar value, then we go back, the matrix go back to the original status. And in case of the third operation, I'm considering I multiply any number, even 0, to a certain row and then add it to another row. Okay? Another row. So for example, if I multiply, say, 2, -2 to the first row, what do I get? If I multiply -2 to the first row, you get -2 and -4. Oops. Right? If I add these numbers to the second row, please remember that I'm adding that scalar multiple to another row. So when I multiply -2 to the first row to get -2 and -4, you never add this number to the first row because I'm adding this scalar multiple to another row. So -2 and 4 can be added to the second or the third row, but not the first row. So if I do that, if I add that to the second row, then the first row is not changed. The third row is not changed. Okay? But the third row operation, this type 3 operation multiplies -2 and then add it to the second row. Then second row is consists of 2 and 4. But if I add -2 and -4, you get just a 0. So that is the result of type 3 operation. And here I just added this scalar multiple to a certain row, to another row. But, and this scalar, given this scalar, I can consider the negation of this scalar can be multiplied and then added to the same row. What happens then? I mean, given this 1, 2, previously I multiplied -2, right? What is the negation of -2? +2. So if I multiply +2 to this 1 and 2, you get 2 and 4. If I add this 2 and 4 to the second row, what do you get? You get 1, 2, 2, 4, 3, 0. So I just introduced three types of elementary row operation. Okay? I consider the three elementary row operations. And as I said, those operations, those elementary operations are reversible. In other words, if A is changed to say B by some elementary operation, B can be changed to A by applying the applying an elementary operation of the same type. Sorry about this handwriting. I'm not good at this. Okay. So as I said, if I consider the interchange operation type 1, if you perform the same interchange operation, the matrix B goes back to A matrix. If I perform, say, scaling operation by multiplying 2 to certain row, you can multiply, say, 3 to certain row, you can multiply 1/3 to the same row, then you go back to the original matrix. Now, if I multiply, say, -2 to the first row and then add it to the second row to get B matrix, then when you multiply +2 to the first row and then add it to the second row, you go back to the original status. So this elementary matrix, the elementary row operation is definitely reversible. You can go back to the previous stage, okay? And at that point, all you need is the same type of elementary operation. Okay? So this is an elementary row operation. So we have only three elementary operations. So here is another example. So suppose that A is matrix A. If I interchange the second row of A with the first row, then you get B matrix. So 1, 2, 3, 4 goes to the second row, and 2, 1, -1, 3 goes to the first row. The third row is not changed. So this is the result of type 1 operation, interchange. And as I said, from B to A, if I re-interchange these two rows, you go back to A matrix, right? So this being reversible is a very important property of elementary row operation. Now, given A, if I multiply the second column by 3, then this 210 became 630. So this is the result of type 2 column operation. Now, given this C matrix, I can go back to A matrix by multiplying 1/3, the reciprocal of 3 to the second column. Then you go back to A matrix. And given this A matrix, if I multiply, okay, if I multiply 4 to the third row of A and then add it to the first row. So if I multiply 4 to the third row, You get 16, 0, 4, and 8. So you add these numbers to the first row entries. Then 1 plus 16 is 17, and 2 plus 0 is 2, and 3 plus 4 is 7, and 4 plus 8 is 12. So only the first row is changed, but you do not alter the second or third rows. And from this m, if I multiply negative 4 to the second row, third row, you get negative 16, 0, negative 4, and negative 8. Given this m, if I multiply these numbers to the first row again, then you go back to A matrix. Okay. So, as I said, if any matrix is obtained from certain matrix by means of an elementary row or column operation, then this P can be obtained from Q by an elementary row operation of the same type. Of course, this statement is applicable to even the column operation. So, as I said, this property shows that this elementary row operation is reversible. This is a very important property of elementary row operation. Okay. Given identity matrix, okay, given identity matrix, you can perform elementary row operation or elementary column operation, right? Now, given identity matrix, if you perform one elementary operation on the identity matrix, you get some result, right? This resulting matrix is called an elementary matrix. Okay. And sometimes, especially in this textbook, we will say elementary matrix of type 1 or type 2 or type 3 if that elementary matrix is obtained from the identity matrix by applying the elementary row operation or column operation of type 1, 2, or 3. So for example, given the identity matrix, if I interchange first two rows, you get the E matrix. So this E is called an the elementary matrix of type 1. Of course, you may say this E is obtained by interchanging first two columns. Yes. So E is an elementary matrix of type 1. Okay. So elementary matrix can be obtained in at least two ways, either by performing some elementary row operation or column operation. Okay. But anyway, the so that is an elementary matrix of E is an elementary matrix of type 1. What if I multiply, say, 3 to the second column of the identity matrix? Then F matrix obtained from the identity matrix. So the first and third rows are not changed, but if I multiply 3 to the second row, the second row becomes this. So this F is an elementary matrix of type 2. Of course, as I said, you may multiply 3 to the second row, or you can multiply this 3 to the second column. If I multiply 2 to the first row and then add it to the second row, what do I get? Then the first row and the third row are not changed, but if I multiply 2 to the first row, you get 2, 0, 0, and then add it to the second row, then you get 2, 1, 0. Okay. Or you may say you can multiply 2 to the second column and then add it to the first column. Right? So depending on the viewpoint, so you can consider this EFG as the elementary matrix, okay, of type 1 to 3, corresponding to certain row operations or certain column operations. In our case, I will focus on elementary row operations. I will explain the reason later, okay, but in our case, we will focus on the row operations, not column operations. But anyway, you need to understand both. So E, F, G are elementary matrices of type 1, 2, and 3. Okay, theorem 3.1. Let me just explain this and then let us consider the proof later. So A is on any m by n matrix, and suppose that B is obtained from A by performing some elementary row operation. Okay, so let me give some examples. So suppose that A is, say, 1, 2, 3, 4, 5, 6, 7, 8, and say 0, 0, 9, 10. Okay, now if I, for example, interchange the second row and the third row, what do I get? Then B is 1, 2, 3, 4 in the first row is not changed, and 0, 0, 9, 10 becomes the second row, and 5, 6, 7, 8 will be the third row. Okay, so if I have B obtained in this way, then, so here at this point I interchange it. Then, then when I have 3 by 3 identity matrix, 3 by 3 identity matrix, when I exchange the second row and the third row, what do I get? What will be the corresponding elementary matrix? You get 1, 0, 0, 0, 1, 0, oops, sorry, 0, 0, 1, and 0, 1, 0. That is the elementary matrix corresponding to that interchange operation. Okay? Then the claim is this. The relation between B and this A and E are this. My B, okay, this matrix will be the same as this E times A matrix. That is the claim of this theorem. And that claim will hold for any elementary row operation. Okay. So that is the main claim of this chapter. Okay, and we will talk about in detail on 16th, on Thursday. Okay, for anyway, thank you for listening, and I will show some examples on Thursday as well of the for regarding the exam. Okay, and please do not forget about our exam. Okay, next week. Okay, anyway, thank you for listening, and see you next week, and see you on Thursday.